All right, so let's work these examples on calculating delta S naught reaction, okay? Which naught is how we say that degree symbol, okay? Well, in this case, we're looking at the production of ammonia, okay? So nitrogen gas plus 3 moles of hydrogen gas plus 2 moles, or goes added together, give us 2 moles of ammonia. All right, so let's look at our piece of paper. First, let's consider the equation that we're going to be using. So delta S naught reaction is equal to the sum coefficients times the standard molar entropies of the products minus the sum of, again, the coefficients matter, the standard molar entropies of the reactants. Okay, so let's consider in this case that we only have one product. We have 2 moles of it, but we have 2 moles of ammonia, so we need to know the standard molar entropy of ammonia, minus the sum of the reactants, and we have 2 of those. We have 1 mole times the standard molar entropy of nitrogen, plus we have 3 moles times, let's tilt this up a little bit. All right, the standard molar entropy of hydrogen. Okay, so basically what we need to do from here is we need to just plug in our numbers. So we have 2 moles times, if you look at the slide, the standard molar entropy of ammonia is 192.5 joule per mole Kelvin, which you see that the mole cancels, right? So we're going to end up with joule per Kelvin, which is the unit of entropy, minus we have 1 mole times the standard molar entropy of nitrogen, which is 191.5 according to the slide, joule per mole Kelvin. Again, moles are canceling, plus we have 3 moles times the standard molar entropy of hydrogen, which is 130.6 joule per mole Kelvin. And again, moles are canceling. So at this point, all you need to do is do a little bit of plugging and chugging in your calculator. All right, so it's 2 times 192.5 minus, open parentheses, 191.5 plus 3 times 130.6. We're going to close parentheses. And when we hit enter, we should get, center the computer better, negative 198.3. Negative 198.3 joule per Kelvin. Now let's talk about this number a little bit. Number one, it's negative. You should have been able to predict that from just looking at the equation itself, because we're going from 4 moles of reactants to 2 moles of products, which means we have definitely diminished the entropy in this, so it should be negative. So if you got a positive number here, that should have been a red flag that you did something wrong. Okay, so the negative makes sense, and then the number, you kind of just have to assume that you did it right. Okay, all right, so now there's another example on the slide. Okay, so it's talking about the decomposition of, or the standard molar entropy for the reaction of the decomposition of water. In this case, without doing any math, predict if you think this number should be positive or negative. So I give you a couple seconds to think about it. Should this delta S reaction, should it be negative or positive? You're going from 2 moles to 3 moles. So you are slightly increasing the entropy. I would think that this would be a positive number. And in fact, it is. And if you had taken and done the math, so 2 times hydrogen, 130.6, plus oxygen, 205, the sum of that, right, minus 2 times liquid water. If you would have used this number, it would have been wrong, because that is water vapor. What am I saying here? Phases matter. 2 times 69.9. If you had used the wrong water, you would have probably gotten the wrong sign here, okay? So again, knowing the ability to qualitatively predict the sign before you do the math is incredibly important to being able to check your work, okay? So make sure you understand this sort of overarching ideas that we're studying here, and then you can sort of check your numerical work as you go along. All right, so that's how you can calculate standard molar entropy, but let's talk about how we can calculate Gibbs free energy as well. Okay, so try to line that up a little bit better. We can also look at delta G naught reaction, again, where we're looking at the change in free energy at standard states. There's 3 different ways that we're going to talk about this. The first way, we've already talked about. Delta G equals delta H minus T delta S, okay? Or delta G naught is equal to delta H naught minus T delta S naught, meaning if you know your delta H corresponds to standard conditions and you know your delta S corresponds to standard conditions, then delta G should also correspond to standard conditions. All right, so let's look at an example. All right, so here we have the production of sulfur trioxide from sulfur dioxide and half a mole of diatomic oxygen gas. We have been given the heats of formation of all 3 substances, and we have been given their standard molar entropies of all 3 substances. Notice for oxygen, it has no heat of formation because you don't have to form it because it's a standard state, but it does still have an entropy. Why? Because we're not at 0 Kelvin. So it has to have an entropy. All right, so to do this one, we got to figure out delta H reaction, then we got to figure out delta S reaction, then we can plug it in to delta G equals delta H minus T delta S. All right, so let's go to our handy dandy piece of paper. All right, okay. All right, moving on. Okay, so let's do delta H first. Delta H naught reaction is going to be equal to the sum of the heats of formation of the products times their coefficients minus the sum of the heats of formation of the reactants times their coefficients. Okay, so in this case, it's going to be equal to, you have only one product and you have 1 mole of it, times the heat of formation of SO3, which is negative 395.7, and that's kilojoules per mole, minus, we have 2 reactants, we have 1 mole of SO2, which has a heat of formation of negative 296.8 kilojoules per mole, plus we have another reactant that we have a half mole of, but what's the deal with this one? The heat of formation is 0, so it really doesn't even affect our work here, okay? All right, so I'm going to pause the video and go grab my calculator. All right, so we got negative 395.7 times 1, which doesn't do anything, minus 1 times negative 296.8, because really the only coefficient that wasn't 1 in this case was oxygen, and it's not even appearing. So delta H naught reaction is negative 98.9 kilojoules per mole, or you could just say this is kilojoules because technically you could say the moles cancel. Doesn't really matter. Okay, let's just call it kilojoules for the sake of what we've been doing. All right, so now let's do delta S naught reaction. It's basically the exact same thing, so I'm not going to write this again. But so we have 1 mole of our product times its standard molar entropy is 256.8 joule per mole Kelvin, minus we have 1 mole of SO2 times 248.2 joule per mole Kelvin, plus we have a half mole of oxygen times its standard molar entropy, which is 205.2 joule per mole Kelvin. And Now we just need to put all of this into our calculator again. So we have 256.8 minus, go ahead and open parentheses, 248.2 plus a half times 205.2. And I got the delta S naught reaction is equal to negative 94. We'll call it 94.0 for now, just to hold on to the same kind of sig figs. Kilojoules per kilojoules. Is it kilojoules? Nope. It's joule per Kelvin. So I hope that you are seeing your red flag here that you should always see whenever you compare a delta H to a delta S, and that is the fact that delta H is a very large numbers, delta S is a very small numbers, so you are going to have to account for this, okay? So delta G naught reaction is equal to delta H naught reaction minus T delta S naught reaction. Delta H naught reaction, negative 98.9 kilojoules. Minus the temperature. If it's standard state, that's 298 Kelvin. All right? Times what you got here for your entropy, which is negative 94. But we can't use that, right? Because it's not in the same units. So really you need to take this and divide by 1,000 to get it into kilojoules. So this becomes negative 0.094 kilojoules per Kelvin. Okay. And at this point, which, sorry, you can't really see that. Fix the camera. All right, yeah. Now we just need to put that into our calculator. So negative 98.9 minus 298 times negative 0.094. And we get the delta G naught reaction is negative 70.9 or negative 71, whatever. And that is spontaneous. It has a negative delta G, which means it is spontaneous in the forward direction. Now let's go back and let's look at our signs though. Okay? So the sign of delta H was negative, which means delta H says it's going to be spontaneous. But the sign of delta S was also negative. A negative delta S means non-spontaneous. So what this means is this reaction is temperature dependent. At low temps, like 298, it's spontaneous. But at high temps, it's going to be non-spontaneous. And we talked about how to calculate the temperature at which you could do that. You just set delta G equal to 0, and then plug in an X for your temperature. You have delta H, you have delta S, and you just solve for the temperature. And that should be a positive Kelvin. All right. So if you get a negative, it's probably just a sign issue. You can, for the most part, probably just flip the sign to positive and you should be fine. Okay? All right, so that's going to be the end of this video. We'll pick up in the next video with more ways to calculate delta G naught reaction. See you in the third video.